During the spring semester of 2020, we were sent home from school and tasked with proceeding with our ENG80 project. Our locations across the U.S. provided opportunities to measure a variety of environments. We were all shipped home to Eugene, Oregon, Boulder, Colorado, Houston, Texas, and McLean, Virginia. This presentation will detail our analysis of data collected across the U.S. First, we will discuss the engineering objectives of this project, as well as provide some background on the first principles that governed our hypothesis. Next, we will move into sensor selection, circuit design, and discuss how we validated our data. Lastly, we will discuss the relationship of environmental parameters studied in this data collection.
The primary objective of this project was to determine the relationship between water vapor pressure, temperature, and illuminance. Our second objective was to implement knowledge of sensor selection and circuit integration learned during the first half of our ENG80 coursework. In simple terms, illuminance measures the intensity of incident light on a surface normalized to human perception of brightness. In the context of this project, illuminance is used as a quantitative measure of solar radiation. About 54% of solar energy passes through the Earth's atmosphere and reaches the surface. While some of this energy is reflected and some is absorbed, all of this energy contributes to the warming of the Earth. Consequently, we anticipated that higher illuminance will result in higher temperatures.
Vapor pressure is the partial pressure of water vapor in air and can be expressed as a function of relative humidity and saturated vapor pressure. Saturated vapor pressure is the maximum amount of water vapor that the air can hold and increases non-linearly with temperature as shown in the graphic. Vapor pressure near Earth's surface is generally less than the saturated vapor pressure. This means that the rate of evaporation of water is greater than the rate of condensation. As temperature increases, the rate of evaporation increases as well. As more water is evaporated, the concentration of water in the air increases, as does vapor pressure. Consequently, we anticipate that higher temperature will result in increased vapor pressure.
An NTC thermistor was chosen to measure temperature, a DHT11 module to measure humidity, and an IR phototransistor to measure illuminance. A thermistor's resistance changes with temperature. The resistance of the thermistor was extracted by placing it in a voltage divider circuit. Using the Steinhardt equation, resistance was converted into temperature. The DHT11 module performs a resistive type humidity measurement and an NTC temperature measurement. The module outputs a digital signal containing integer values for both measurements. This requires minimal circuitry. These equations were used to calculate vapor pressure from the DHT11 output. Phototransistor currents vary linearly with increasing illuminance. By placing the phototransistor in series with a fixed resistor, the current across the phototransistor can be determined with Ohm's law. The illuminance from this current was calculated using an approximation of the linear relationship between current and illuminance specified by the phototransistor's datasheet. The phototransistor chosen to measure illuminance was sensitive to infrared spectrum light. As illuminance is normalized to human perception, and therefore visible light, the values obtained from the phototransistor did not fall on the magnitude of illuminance that we anticipated for testing conditions. In order to remedy this, additional data was collected with a visible spectrum photoresistor, and this calibration curve was developed.
In addition to collecting measurements from our sensors, reported values from the National Weather Service, represented here by black curves, were recorded to validate our sensor readings, the colored curves. While the measured values were not always the same magnitude as the reported values, they mirrored reported trends. This indicates that our sensors provided reasonable representations of temperature, vapor pressure, and illuminance trends.
The linear relationship of aggregate vapor pressure and temperature data is displayed on the right in black. The location-specific regressions are displayed individually on the left and with the aggregate fit on the right. Though the different location fits all exhibit a positive linear relationship, different locations experience varying ranges of temperatures and vapor pressure, and may also exhibit a more or less drastic change in vapor pressure due to the same change in temperature. This consistent trend across locations suggests that vapor pressure and temperature have a positive linear relationship.
As displayed in the plots separated by location, illuminance and temperature also exhibit a positive linear relationship as anticipated. On the right, the overall linear relationship is displayed along with the linear regressions for each location. The slope and vertical displacement of the aggregate illuminance versus temperature curve is subject to change if other locations are tested. Moving forward, this analysis could be widened by collecting data across a larger variety of locations at different times of year. Additionally, future investigations could focus on determining the validity of a direct dependence between vapor pressure and illuminance, beyond the interdependence of the two properties on temperature.